Hello friends, welcome to the video lecture of Internet of Things TYBSc IT Semester 5. Let us start with the first chapter of this unit, that is moving to the manufacture. The contents are displayed on the screen. At this point, the initial prototype must be clear to you, that is in terms of electronics, physical design and online platform. This is the stage of production of your device. But before thinking about scaling up the production of your device, you should think about what exactly you will be producing. There can be three choices if you want to make your device as a product in market. Firstly, you can make a kit that your customers can assemble themselves. Another choice is you can make a ready-made electronic board which users can use as a sub-assembly in their own projects. And the last option can be you can make a full-fledged product complete with its housing, instructions and even packaging. If you want to sell your idea as a product, provide it in terms of a kit. People will prefer buying these kits because someone else has done the hard part of selecting and sourcing the right components and putting them together with step-by-step guide. Prepare kits which tend to piggyback on existing microcontrollers, and that in the form of standard format plug-on board. This makes sense because it reduces the support overhead for the kit provider. Also document the build process and provide it in terms of manual. Though you must have made the final prototype, it is still a bundle of components and wires plugged into a number of breadboards. You can go one step further by soldering things up, but since your product is going to be handed over to the end user, converting your solderings into a PCB makes sense. You can design and etch your own custom PCBs. PCBs offers you more options on how to lay out the circuit and makes it easier to solder up, as the only holes in the board will be those for the components. You need some software to help you design your PCBs. Fritzing is a free and open source design package aimed particularly at beginners in PCB design. When you are done with your design, you can export it for manufacture as a PCB. KiCad is another software which is open source and have more traditional workflow. It has more comprehensive library of predefined parts. So what makes up a PCB? PCB is made up of number of layers of fiberglass and copper. Both are sandwiched together in the board. Copper is a conductor and forms the wires to connect the components in the circuit together, while fiberglass acts as an insulator between different layers of copper. Sections of copper are etched away using chemicals. Single-sided boards have only one layer of copper, usually on the bottom of the board. Double-sided boards have two layers of copper, one on the top and one on the bottom. Complicated circuit needs more layers on board. Professionally manufactured PCB undergo different processes to make it more simpler to use. It starts with designing the schematic view of your PCB. This step lets you lay out the components logically and make the necessary connections without having to worry about exactly where they will sit in physical space. One can use different software packages to design these schematics. When you are happy with the schematic design of your board, you can proceed to layering out the physical board. There are no hard and fast rules on how to arrange the board, but it makes sense to keep together groups of components that constitute an area of functionality. For example, components related to power supply can be kept together for more logical layout. You can manufacture your own PCBs by using etching boards technique. You can also perform it at home. There are some readily available kits that provide all that you need. It starts with getting the PCB design onto the board to be etched, which involves printing out the design using CNC mills. If you want your PCB to be more professional, There are many companies who can manufacture the boards for you. The price for getting the boards made varies based on the complexity and the size of the design. After your PCB have been manufactured, you still need to get the components soldered onto them. For small runs, you can solder them by hand. You can also use surface mount assembly. After your boards are ready and properly assembled, you need to test them. Automated assembly process already provides few testing steps. Assembly lines can include automatic optical inspection, where a high-resolution camera inspects some aspect of the board and its components. After this, boards need to pass the functional test too. The functional test just involves powering up the board as it will be used in the finished product and ensuring that it does what it is supposed to. Mass production of cases and other fixtures are part of prototyping physical design. One can use laser cutting or 3D printing techniques to create these fixtures. Use more machines than people in your assembly process, as machines are more cheaper than people. Your Internet of Things product will be incomplete if it fails to meet the relevant certification or regulations. These regulations are there for good reason. They make the products you use day in, day out safer for you to use. Make sure that they work properly with complementary products from other suppliers too. One should ensure that the product doesn't emit lots of unwanted electromagnetic radiation and interfere with the correct operation of other devices nearby. The most common regulations and certifications are from CE, FCC, and UL. CE is marked for meeting European standards, FCC for US Federal Communications Commission regulations, and UL for Independent Testing Laboratory UL's test. Mass manufacturing of your product may incur sizable upfront cost. You need to raise enough money upfront so that you can manage manufacturing project easily. Your PCB manufacturing process requires considerable amount of money. The setup and tooling process, such as injection molding, can be more money demanding. You need to record all this cost in BOM, which is Bill of Materials. Producing a physical thing as a prototype and manufacturing a product are two different things. Your product has to be polished before it can be exposed to the real world. This polishing involves checking for correctness, maintainability, security, performance, and community. The deployment involves both the embedded device and the online services that you have built need to be properly checked. Deployment is copying software from a development machine to where it will be run. In such IoT embedded cases, firmware running on the microcontroller will be done only once during the manufacturing. Then the software will be flashed to the device which we are going to hand over to the end user. You also need to flash the software for online services. There needs to be a provision of updating the code for improving the functionality and design. As your product is publicly available product, your software has to do what you claimed it would and do it efficiently and safely. That's why testing your code before it is deployed is an important step in helping to avoid such a situation, and your chosen language and development framework will have standard and well understood testing environments to help ease your task. It is critical to consider the consequences of a mass market product being attacked. There are some guidelines to keep your device secure, like keeping your servers up to date with the latest security patches. While scaling up the software, it is worth checking whether it will be fast enough to handle a large number of users. One should focus on running web application with appropriate standard infrastructure which is good enough for most performance related problems. If the web service of your product is running on modern framework, then it is easy to scale up by deploying the code onto more powerful machines. Finally, your product needs to satisfy user community too. At minimum, you need a support email or a bug reporting tool, but you will probably have a presence on various social media forums. Using different forums, introductory videos, tutorials, blogging are good ideas to keep the user community updated. The next chapter in this unit is all about ethics. A technology is a two-way sword. One can easily say technology destroys job. Technology disconnects humanity from ancient traditions. It encourages us to become lazy and unhealthy, and it tempts us into thinking we are like gods. But technology is also a progress. It will save lives and feed the starving. It will also make us happier, healthier, safer, and better educated. Take a moment to reflect on your own stance to technology in general. It may be that you are generally anti or generally pro technology. It is also possible that you are optimistic about some classes of technology, but pessimistic about others. As Internet is a massive open publishing platform, privacy is seldomly maintained. Everything you write might be visible to anyone online. From your status, what you ate for breakfast, your blog post about your work, from articles about your hobbies to Facebook posts about your parties with friends, etc. There is a value in making such data public. The story told on the internet becomes your persona and defines you in respect of your friends, family, peers, and potential employers. As Internet of Things are about things which are rooted in different contexts than computers, it makes uploading data more ubiquitous. For example, even innocuous photos can leak data. With GPS coordinates embedded into the pictures, metadata and analysis of your Flickr or Instagram feed can easily let an attacker infer where your house is, your work is, or even your children's school is. Most of the time, data related to you is being controlled by someone else. For example, CCTV footages. In those footages, you are the data subject, but you cannot control which data you want to pass on. In another case, if you are gifted a wear dial or a goodnight lamp, is there an expectation that you use it even if you don't really want to? Technology itself doesn't cause any controlling behavior. It could easily be applied by a spouse, parent, or employer in ways that manifest themselves as abusive, interfering, or restrictive. As a matter of privacy, there are almost always good reasons for giving up some control to the user. Already, companies and organizations are looking at mashing up data sources and apps and may start to offer financial incentive to use Internet of Things devices. This is even worse because nowadays surveillance equipments are cheap and the processing power required to analyze the mountain of data produced by these equipments is getting more accessible. The internet destroys the state. This is a hard and uncomfortable scenario to imagine. When a technology is referred as disruptive, it means that it affects the balance of power. It is being claimed that Internet of Things will transfer power away from the citizens. These devices, with the help of robotic network, can become self-healing networks. Transferring power from humans to machines can be disruptive. One fascinating feature of modern internet life is crowdsourcing, from knowledge to funding projects to work. The original idea of crowdsourcing was, instead of making data public, let people make data for a project. There are 5 critical requirements observed in Fisher's original definition for a sensor commons project. According to him, every project must gain trust, become dispersible, be highly visible, be entirely open, and be upgradable. Trust is largely about the way that an activist project handles itself beyond the seemingly neutral measurements, understanding local issues, being sensitive about the ways that the sensor network itself affects the environment. Becoming dispersible means spreading the sensors throughout the community. Getting mass adoption will be easier if the proposed sensors are inexpensive. Being visible involves explaining why the project sensors are occupying a public space. Being honest and visible about the sensor will help to get trust in the project and also advertise and explain the project further. Being open is perhaps what distinguishes the sensor commons from a government project the most. Government data sets are often entirely closed, but the data that is released from them will be given a lot of attention because of the rigor and precision that their sensor projects will have. Finally, the project should be designed to be upgradable, to enable the network to remain useful as the needs change or hardware gets to the end of its working life. The project needs to be an open project. There are some classic environmental concerns about the production and running of the Internet of Things itself. Creating the object has a carbon cost, which may come from the raw materials used, the processes used to shape them into the shell, the packing materials, and the energy required to ship them from the manufacturing plant to the customer. The cost of these emissions need to be considered. The electronics contained in a thing have their own environmental cost. Buying PCBs locally or from a foreign manufacturer affects the carbon cost of shipping the complete unit. Considering the potential cost savings, even a responsible manufacturer may find it reasonable to offset the extra carbon emissions. In the digital world, moving data rather than physical objects is faster, is safer, and has a lower environmental cost. But running the internet has cost. The electricity to run the routers and the DNS lookups, plus establishing the infrastructure, laying cabling across the sea, setting up microwave or satellite links, and so on, as well as the cost of transferring the data across the internet. Running your own web server uses power. Sometimes for these services, you pay extra to offset your emissions. Compared to a simple physical object, an instrumental Internet of Things device does seem to use vastly more resources in its production, daily use, and waste disposal. Such instrument is now cheap enough to put everywhere. It seems as though the mass rollout of the Internet of Things will only contribute to the environmental issues. From a more optimistic point of view, it is true that the number of internet connected devices will be exploding in the coming years, is spurring massive research into low power efficient chips and communications. Technology did change the world massively, but without the changes that disrupted and spoiled one world, we wouldn't have arrived at a world our world where magical objects can speak to us, to each other, and to vastly powerful machine intelligence over the internet. As a massively interdisciplinary field, practitioners of Internet of Things may have an opportunity to contribute to providing moral leadership in many of the upcoming ethical challenges. There are two contrasting points one should always remember while designing Internet of Things. That is, everyone is not you and you are not special. And this makes us realize that different technology matters differently to different people. The definition of Open Internet of Things can be summarized in three things. The first is accessibility of data. The second is preservation of privacy. And the third one is transparency of process. The Internet of Things brings the gathering and collation of data into the everyday world and has real consequences on individual privacy and power. Technology often creates new possibilities with one hand and new problems with the other. As technologists, we don't have to see these concerns as prophecies of doom, but as a reminder to consider our responsibilities while we are engaged in designing and building our magical objects to delight our customers and bring up profit or amusement. Thank you for watching this lecture series.